Welcome to the webinar, Wolfram Technology Webinars, Interactive Data Science, Visualizing Data with Dynamic User Interfaces. Let me first introduce myself and my company. My name is Thomas Paunweiser. I am working at the Unisoftware Plus GmbH, which is a company based in Perg in Austria. We have around 20 employees. 4 of them are theoretical physicists from their background, and we have more than 10 software engineers. Unisoftware Plus is a Wolfram technology reseller. Our main Fraunhofer Gesellschaft in Germany. And we provide license and installation support, as well as technical support in using Mathematica. Our other business areas are data science, industrial mathematics, and financial mathematics. Moreover, we provide consulting and project partnerships in data science projects and Wolfram technology-related projects. If you want to know more information, please visit us at our homepage or write us an email to office@unisoftwareplus.com. So this brings me to the main part of the webinar. First, let me give a small motivation. Why do we care about dynamic user interfaces? How can they help in, say, data science? First example I have here is, consider you have imported some example data. In this case, I'm generating some random data. And you can simply plot it using, for example, the mathematical function listline plot, and you want to inspect the data more closely at a certain interesting point here, an outlier. Unfortunately, Mathematica doesn't provide a direct possibility to zoom into this region. You can, for this purpose, use, for example, use a manipulate construct here to dynamically adjust the X range of the plot using this interval slider. And so you can navigate around your data and inspect the data more closely. This is just one first example where dynamic user interfaces can help. As a second example, consider, again, you have imported some data and you want to do some pre-processing, for example, smoothing, but you do not know which kernel radius to use beforehand in order to achieve a good smoothing, not too smooth and not too spiky. You can use here, for example, a dynamic control to immediately see the result of the kernel radius you choose. And then if you have got the right value, you can go on with your data analysis. Okay, how do we create dynamic controls within Mathematica? There is one very high-level construct, which we have seen in the 2 examples I just showed you. The first, this construct is called manipulate, and the function is very similar to the table function. But probably you all are familiar with the table function. In this case, I'm creating just a list of 20, the first 20 integers. If you do pass the same arguments to the manipulate function, you see one element of the list at a time with an additional control, a slider in this case, which shows you the appropriate value, the according value. Of course, you can display more meaningful data, not only primitive variables as in this example. For example, you can use a plot which has a free parameter omega, and you can interactively change the parameter omega in the range from 1 to 4. If we evaluate this example here, we see the plot with an initial value of omega equals to 1. And we can dynamically adjust this value and see the immediate result in the resulting plot. Of course, you can use manipulate with more than one single variable. In this case, I'm again using a simple plot of a cosine, a sine function, and a linear combination of those two, where you can just dynamically adjust the parameters a and b and immediately see the yellow curve, the linear combination. Additionally, you have the possibility to provide a custom label here. It's the same example we saw before. Instead of omega, I'm now displaying here the label angular velocity. And it depends. There are a variety of control types which manipulate provides by default. In this example, I've listed some of them. So this manipulate uses 1, 2, 3, 4, 5, 6, 7 variables, and each of them is an example for a different control type. So the first control type we have already seen. If you provide a minimum and maximum value, you get a continuous slider here. And you can see the dynamic output below. If you additionally provide a minimum and maximum and additionally step size, you get a slider with distinct, but discrete values. If you provide a list of elements, you will get so-called setter bar, a list of buttons which you can select. If you use a minimum and maximum as both of them 2D vectors, you get a so-called 2D slider. Can sometimes be handy if you provide a list of true and false, you get a checkbox. If you provide a color, you get a color slider. And if you provide just a simple string or any Wolfram language expression, you simply get an input field. Note that this input field supports arbitrary Wolfram language expressions. For example, square root of 2, if you press enter, you will get this symbolic representation here. You can use also functions here to evaluate it numerically. You can, of course, restrict the input fields to use only strings and not mathematical expressions. More on that you find in the Wolfram language documentation for manipulate and also for input field. In addition to those standard controls which manipulate provides, you can provide your own control by providing here a function. I've done this for an interval slider here. So the interval slider takes as first argument the thing you are manipulating, then it takes the range and a minimum interval size. So if I evaluate this here, I get this interval slider, which is a handy control for, yes, we've seen it in the example at the beginning. By the way, if you have questions, please feel free to write them in the chat window. I will have an eye on the chat window and will try to answer the question as good as I can. Here I have an additional example using just another custom control type. It's a toggler bar, which allows you to select several elements from a list of elements. Note here that the order of the resulting list depends on the order you clicked the elements. So if you want an ordered list, you have to additionally use them a sort, for example, to get a canonical representation of the subset you selected. For a full list of all available controls, you can have a look at the Mathematica documentation. I have put a link for you here. We will provide the slides and also the example notebooks I'll show in this webinar online, so you can download it afterwards. For further reading, you can look also in the documentation. Here I have put the link of 2 tutorials for manipulate, if you want to dive more deeply into manipulate. So this was the first possibility for creating dynamic controls. The second and more low level, I would say, possibility is to use the Wolfram Language construct dynamic. For this, to introduce, let me first define a simple variable and let's inspect its value. Of course, everyone who used Mathematica before will know that this output, the output depends on the variable's state at the time of evaluation of this expression. So if I change the variable value afterwards, the output of the first evaluation here will not change. If, however, I use dynamic around my variable, I will see also the current value of the variable. But in addition, Mathematica, or to be more precise, the Mathematica front end will update the output whenever the variable value changes. So if I just set the variable value here to 3 by evaluating this cell, the current state is also reflected here in this output. You can use dynamic not only for output, but also for input. For example, I can create a setup bar where I pass a dynamic value as the thing which the setup bar should operate on. In other words, if I change here the selected element in the setup bar will update the value of the variable. And we also see it reflected here in this dynamic output. So an additional example, we can use dynamic not only for primitive variable values, but also for arbitrary Wolfram language expressions. So for example, here I always want to see the square of the variable's value. And if I update the value here, the square is calculated. Or in this case, I'm using a number line plot to visualize the point I have selected. So the takeaway from here is you can use arbitrary Wolfram language expressions within dynamic, and the output will be updated whenever any variable changes which is used by this expression. There are some things to know about dynamic for understanding it, how it works. First thing is that dynamic has the attribute hold first. If I request a list of attributes associated to dynamic, then we see that hold first appears as first element in this list. And what this means is that the argument of dynamic will not be evaluated immediately by the kernel. In fact, the Mathematica front end will decide when to reevaluate the expression wrapped within the dynamic construct. And when does this happen? The output is updated whenever a variable the value of a variable is changed, which is used within the expression. So the expression within the expression passed to dynamic contains a variable which is let me start over here. So the dynamic output changes whenever a variable is changed, which is used by this expression. And moreover, it is only updated when the expression is currently visible to the user. So if you, for example, try the following, x equals 1, and dynamic y equals x squared. And we want to see the dynamic value of y. And we set x now to 2. Then this dynamic here updates the variable y, but it does it only when it is visible. So if I'm hiding it from the user interface, this can happen just by scrolling, or okay. Obviously, it doesn't happen by just collapsing this cell. But the point is, when you scroll or minimize the window, such dynamic updates are not done. And this can have unintended effects when using it dynamic in this way. So expressions with side effects within dynamic constructs are not are discouraged. This is the takeaway from this slide here. One more thing to know is that the difference between synchronous and asynchronous dynamic evaluation. The Mathematica frontend and the kernel are two separate processes which communicate via three so-called communication links. The main link is used by the frontend to enqueue expressions to be evaluated by the kernel. So it sends the expressions to the kernel, and the kernel in turn uses the so-called service link to send back the evaluated results to the front end. And the third link is the so-called preemptive link. It is used by the front end to evaluate expressions related to user interface rendering. Such evaluations generally are fast, which means fractions of a second. And for this purpose, Mathematica uses synchronous communication, which means that while such user interface evaluations are ongoing, the front end will not be responsive until the kernel returns the result. For more information on this, on the architecture of Mathematica using those different links and synchronous and asynchronous evaluation, you can have more precise look here. I've put the links to the Wolfram documentation here. So by default, dynamic uses synchronous evaluation. So communication is done using the preemptive link. For the preemptive link, there is usually a shorter time limit for evaluations. In other words, long evaluations will usually abort within a dynamic context. Here I have an example. Again, a setup bar where we can set a variable value. And here in this dynamic, I am simulating a long-running evaluation. So it takes 10 seconds. It pauses 10 seconds and then returns the variable value. Okay, we see that after approximately 5 seconds, Mathematica says this evaluation lasts too long and it will abort it. However, unfortunately, this mechanism of aborting long-running dynamic evaluations does not always help, because sometimes it may happen that you run into some infinite update loop. Then, in this case, the Mathematica frontend can freeze irrecoverably. You can, however, also use asynchronous evaluation by setting the so-called synchronous updating option. I've done it here. It takes 10 seconds, and we will see then the output 6. If I change it, it takes another 10 seconds to update again. So in this case, you see I can move the cursor around and everything stays responsive while this thing evaluates. And in general, the takeaway from here is that for evaluations which last longer than, say, half a second or so, it is a good idea to use asynchronous evaluation. So for developing reusable dynamic controls, it's important to keep variables bound to local scopes. Wolfram Language provides several scoping constructs. 3 of them I've picked out here, which have subtle differences. The block construct, for example, reuses one or more symbols from any outer scope, but temporarily forgets all values and definitions associated to those symbols, such that within the block construct, the symbols only look like new unique symbols which have no values and definitions associated. In contrast to that, the second scoping construct module creates unique namespaces for the symbols of the module. The symbols are indeed unique within a Mathematica kernel session. For developing dynamic controls, however, it is recommended to use the dynamic module scoping construct, which is very similar to the module construct. However, the namespace is not created by the kernel, the namespace and lifetime of the variables, but by the front end. As I said, dynamic module is the preferred way to define variables which should be used in dynamic contexts. In order to illustrate this subtle difference here, I've created here a module with a single variable x. I'm displaying the variable name, the full variable name of x. We see that it has a generated namespace ID here to make it unique. And I am creating here a slider for updating the variable, and I'm displaying the current value. So this is nothing which is too surprising here. If I copy and paste this output here, we see that those two controls I created are coupled together. They both operate on the very same variable x. For dynamic controls, however, it is often better, or usually more helpful to have decoupled contexts. So if I copy and paste this control here, we see that those two indeed are not coupled anymore. Moreover, the dynamic module also has additional advantages. When saving the notebook, for example, Mathematica will also store the current values of all dynamic variables which are used in the dynamic construct. And if you reopen the notebook, your dynamic controls will have the same state as they had when you last saved them. A last scoping construct which can be helpful is the with construct. Strictly speaking, it is less a scoping construct, but more a replacement for the replace all command. It's a more readable form, so to say, for replace all. Consider, for example, if you have a list of parameters. Here I have 5 random numbers, and I want for each of those numbers to have a slider to manipulate it. I can do it by creating for each a table with the corresponding index and a slider with the corresponding list element. So if I want to adjust the first element here, okay, I should also add the output here. You can see that it works for the first element, the second, third, fourth, and fifth. For this to work, I need this with construct here, which again, remember that dynamic has the attribute hold first. So if you do not use with here, the I remains unevaluated. I have an example here. So if we just create a table with using dynamic list I, this I will not be replaced here. It will generate a list with a symbolic name I, and it will not work. If, however, you use the with construct, with I is equal Y, the with construct will replace all green I's with the current value of the blue I. So you get the list you wanted, list 1, 2, and so on. So this is a trick to create multiple controls for multiple parameters. So for further reading, I have put some links here. And the second part of the webinar will focus more on practical examples. I have chosen 2 practical examples, which I want to show you. The first is the zoom control. Consider any arbitrary 2D graphics object like a plot, a list plot, or a graphics object, or this more special Mandelbrot set plot here. Really, it would be nice if Mathematica supported zooming here. So if you just clicked on it and could draw a rectangular region to zoom into an interesting region here. We can create such a control, as I have done here. I will come on how this is done in a minute. And just to give you an idea on what it does, I have an example here, a simple plot. And if I pass this plot to my zoom control function here, I can really click on the graphics object and draw a rectangular region to update the plot range of the plot. If I just click without dragging, it will reset the graphics to the original plot range. So this works. It also works for example, a Koch curve here. So what do we need to create such a control? First of all, I'm defining here a custom function called zoom control, version 1. which takes an arbitrary 2D graphics object as argument and with several uses internally several variables in a dynamic module. The variables used are the initial plot range. It is set to the plot range of the graphics object, which is extracted using absolute options and lookup. The second thing which happens is that the plot range, the current plot range, is set to the initial plot range. Moreover, the zoom control functions keeps track of two 2D points, P1 and P2. P1 is the point where the mouse cursor has been clicked, and P2 is the current point while the mouse cursor is dragged. We have three custom functions here: mouse down, mouse moved, and mouse up, which are called when the mouse button is pressed, when the mouse is moved, and when the mouse button is released. When the mouse button is down, we set the first point here to the current mouse position on the graphics object. When the mouse is moved and P1 is still null, this means the mouse button has not yet been pressed, so the mouse is just hovered. Nothing happens. In other words, P2 is set to null, or it is already null. But if the mouse has been pressed and the mouse is therefore dragged, P2 is set to the current mouse position on the graphics. Finally, in the mouse up function, I am deciding if P2 is null. In this case, the mouse just has been clicked without dragging operation. In this case, I'm resetting the plot range to the initial plot range. Otherwise, if the mouse has been dragged and the non-empty rectangular region has been drawn, I am setting the plot range to the corresponding region here. And finally, I'm resetting P1 and P2 to null. Now comes the part where we actually display the graphics. We do it using the show function. The show command function allows you to add additional plot graphics options to the graphics. In our case, we use a custom epilogue here, which allows to draw on top of the given graphics object some additional graphics primitives. In our case, if P2 is null, therefore no zoom region has selected yet, we draw nothing, an empty list of graphics primitives. Otherwise, if P2 is not null, we have a non-empty zoom region selection. Then we draw a blue dashed rectangle corresponding to the points P1 and P2. Finally, we adjust the plot range of the graphics object to the dynamic value of the current plot range. The whole thing here within the show expression is wrapped in an event handler, which just is used to call the respective functions when the mouse is pushed down, moved, or released. So if we again try this with our Mandelbrot plot here, we can now see that we can zoom into the plot. But however, the resolution is not very good. The reason for this is that we didn't pass to the Mandelbrot plot a Z-min and Z-max option. So the Mandelbrot plot takes two complex numbers which correspond, to the 2D region to draw. So what we needed to do to make this better is somehow to pass our current plot range to the Mandelbrot plot. How can we do this? For this, we adapt our zoom control version 1 such that it doesn't use an internal local variable for storing the current plot range, but instead we take the variable to use as first function argument in the form dynamic plot range. It is very similar to what you do with for example, slider or other control objects we have seen before. So our new zoom control takes as first argument the plot range to use wrapped in a dynamic construct, and as second argument, the graphics to display. Again, we are setting the initial plot range to the current plot range. Everything is more or less the same as before. We have a small difference here. Instead of show, I'm using here a custom dynamic show function, which I defined here above. The reason for this is that unfortunately, show does not know how to cope with graphics objects wrapped in a dynamic construct. So, and this dynamic show knows how to handle it. If I pass a dynamic graphics to my dynamic show function, I'm using show on the primitive graphics object and wrap it again in a dynamic construct outside. Otherwise, I'm using show directly if it is not wrapped in a dynamic construct. Then I have a second definition here. If I call zoom control without the first argument, I'm creating just a plot range as before as local variable and initialize it with the current plot range of the past graphics object using again absolute options and lookup, and then call the above definition with this plot range here. If we again try it out, we see that for the simple cases, everything stays the same. And for the more complex case of our Mandelbrot set plot, what I'm doing here is create a dynamic module, define the default plot range or the initial plot range I want to have, and then call zoom control with my plot range variable wrapped in a dynamic construct. And what I want to show is a dynamic Mandelbrot set plot with z min and max corresponding to the current plot range. So if I'm zooming here, I can really dive in deeply here in some of the fine details of the Mandelbrot set. Okay. This brings me to my second example, which is more related to data science now. Of course, this zoom control, we will come across it again. Let's first consider, again, you have imported some data you want to visualize. In this case, I have generated some random data. We have an integer index column, a timestamp column, and then 10 variables with more or less random floating point values. For beginning, I'm using just 5,000 data points per variable, which is of course not very realistic, but we will see how we can go to larger data sets later. So if we want to plot this data, we need to somehow massage it so that we can pass it directly to list plot, for example. For this purpose, I have defined a small helper function. And to visualize what this helper function does, let's just evaluate it on our sample data here. It creates for each of the variables pairs of x, y coordinates, where the x coordinate corresponds to the variable index in this case, and the number of variables generated here is just specified by the list of variables passed here. So variables in this case is the list of all variables, but you can also pass here just a subset of variables. If I pass this to list plot, I now get a nice list plot of my sample data, or also a date list plot. It's an example when using, instead of the index column in x direction, the time column in x direction. I can use a date list plot, and I will get a nice date axis here. And this plays nicely together with the zoom control, which we defined before. If I'm using zoom control here, I can zoom into the graphics and inspect details nicely. Now let's make the graphic here more interactive. The first thing which we want to do is to make the list of variables to be plotted selectable. For this, we define for each of our variables a fixed color. And we can use a manipulate to select the x-axis variable and the list of y-axis variables using, again, the toggler bar control function here. So, for example, I have now a control where I can zoom, and I can, for example, remove this yellow curve. It's variable 8. It's not so interesting, for example. But unfortunately, also this variable 2, for example, the zoom region, this does not persist. If I change the list of variables, I will get back to the whole plot range. If we want to make the current zoom range persistent, we again define the plot range to use outside of the manipulate construct in a dynamic module. So I'm defining this here. And in addition, I want to create my zoom control only once and not every time the manipulate updates. You can do this using a construct called refresh with an argument none. It's, so to say, the inverse operation to dynamic. If you have within a dynamic context something which should be evaluated just once, you can use the refresh none construct. So I'm creating my zoom control only once with the plot range from outside, and as graphics element, I show my dynamic list plot. If I evaluate this here now, I have the same dynamic control. I can zoom into it, and I can remove again the yellow curve. But now, as the variable is outside of this variable 8, yes, is the yellow curve. The zoom range persists. Okay, one additional thing one could do is, instead of using a separate dynamic module scope for a plot range variable, you could also reuse the dynamic scope of manipulate itself. For this, you can define the plot range as argument to manipulate with a control type none. Then this plot range will just exist within the manipulate, but no control will be shown by manipulate for this plot range. So it has the same effect as the construct above, but could be considered somewhat more elegant for this use case. Okay, that's all nice, but 5,000 data points per variable is not really that much. So let's create a slightly larger data set with 50,000 data points per variable. And now let's see how long listplot needs to plot the data. For 500,000 data points, it already takes a while. And the question is, how can we improve the performance in this case? The first idea which you can have is not to use listplot, but an ordinary plot with interpolating functions. It's lasting quite long. So it took 31 seconds to plot just 500,000 data points. This is really quite long. Sorry, I have lost where I was. I think I was here. We've seen it took 31 seconds to plot 500,000 data points. What we can do now is to generate for each of our variables a so-called interpolating function using the interpolation. And in order to be able to pass it to plot, we additionally need to create from the interpolating function expressions which have what happens. This is quite strange. Oh, I see. I have X in the scope defined. So what we need to pass to the plot function is not the interpolating function itself, but an expression with a symbolic X where the plot function should be evaluated. And then we can pass it to our ordinary plot. So in this case, 31 seconds compared to 4.5 seconds, it's significantly faster. And we can again use this for dynamically showing the data with zoom control and selection of variables as before, but now with 10 times more data points as before. Still 50,000 data points is not that much for realistic purposes. So let's create a still larger data set with 1 million data points per variable. So 10 million in total. So here already the generation of the sample data takes quite a while. If we again use our approach with interpolating functions, also this approach is reaching its limits now, because plotting the data in this way already also takes a while. What can we now do about it? Well, of course, we trivially could use mathematical built-in functions such as downsample or array resample in order to simply throw away data points and plot just a subset of data points. But this has the obvious drawback that outliers are potentially lost and not displayed in the plot. Therefore, another better approach, which I have implemented as example here, is to partition the data into sublists. Okay, 43 seconds for the interpolating function approach. It's also too long to be practical. So the approach is that I partition the data into sublists, and for each of the sublists, I compute its minimum, median, and maximum. And instead of displaying all data points, I'm just displaying the median values with a min-max band around the median values. As a first helper function for this purpose, I have defined a so-called list digest function here. I'm just showing you what it does. For this particular list, the median of obviously is 13, and the minimum is 2 below 13, 11. I don't know if you can read it. And 7 above 13 is the maximum. I can also visualize this in a number line plot. And similar to the plot data function I've defined above, I'm now bringing the data into a form using those around values, which are understood by list plot. So again, to give you an idea what this reduced plot data function does, it creates for each variable pairs of x and yes, such an around value representing the sub-interval at this point x. I can pass this now to list plot and get a nice plot with bands. And it should now be somewhat faster. Okay, 9 seconds is also not too fast, but still better than 43 seconds. Of course, you can adjust the number of sublists to make it still faster. And as a final exercise, I have also used this again within dynamic control. And now you have a control where you can display 10 variables with 10 million data points each, and you can still zoom into the graphics and have kind of an interactive visualization here. Note that the refinement of the data lags somewhat behind, but if you wait long enough, the data will be updated. And if you zoom into the data deep enough, you will finally see the original data series. Without error bands. Okay, this brings me to the end of my presentation. Do you have any questions?